All right, class. Today, um, remotely, I am going to be talking about the internet and how the internet works. We're going to start out with some fundamentals of the internet. We're going to talk a little bit abstractly and then to get into a little bit more specifics in terms of how things work. Um, but to describe things a little bit generally, let's first talk about communication. We've started the class talking about communication between processes. So one of the concepts that we talked about in the first weeks was the idea of inter-process communication on the same machine. For example, if I have the process echo sending its output to bin cat, then those two have a way of communicating, but what happens is the kernel is what's helping facilitate that communication between processes. Okay, but now we're talking about when we get into internet communications, we're discussing what happens when a process on one machine communicates with a process on another machine. And in fact, this is exactly what happens when we do something like a web server. So you have a client that's an application on your machine, like a web browser, that is now interacting with a process on some other machine, which is acting as a web server, and those two are somehow to communicate. Those two are somehow able to communicate such that the machine that's running your browser is sending some communications indicating what it wants. Okay, what sort of resource it wants. It might be a web page, it might be a piece of JavaScript, it might be an image, and then that server is somehow communicating back the content that the client had requested. Okay, so you have this sort of communication, and that communication, how it's defined, is somewhat arbitrary. Okay, but let's take a step back now and talk about how the internet is set up, and then we'll go into more specifics in terms of how this actually works. Okay, so first of all, let's go to let's break this down a little bit. So we have some long message, and it might be something related to, again, the web. It might be email. It might be some sort of messaging app. Whatever it is, it's basically a series of bytes, just like anything else when we're discussing computers. So what's going to happen is we're going to take that message and we're going to divide it up, however big that message might be, and we're going to divide it up into packets, okay? And so we're going to chunk those up, and those packets are going to be traversing the internet from one host on the internet to another host somewhere else, okay? And so we refer to this as packet communication. But let's talk about how that actually happens, okay? So you're connected. When you start up your laptop and you get some sort of network configuration, you find yourself on a network, okay? And there's, here you are, we're going to call you host A, and then way over here on the internet, on the other side of the internet, we have some other host B. And again, this might be a web server, it might be a mail server, it might be even when you're doing SSH, it could be the server that you're running into, that you're logging into via SSH, something like that. There's some other process going over there. Okay, just the fact of how do we even get these packets, these messages that we've broken up into smaller sizes. How do they get there? How do they get back? So that's what we're going to talk about now. Okay, so the idea is, and we oftentimes draw everything in between as sort of a cloud, and then we have A sort of talking into the cloud, and then there's magic happens, and then your packet suddenly arrives over at B. Okay, so let's sort of pull away from that cloud. So the first thing we'll talk about is that A is somehow connected to what we call a local area network. Okay, and simply what that means is that when it gets connected, there's certain other machines. So for example, in your wireless network at home, many of you probably have a wireless router, okay, and when you plug into that, all the machines on that same wireless router would be in your same local area network. And in that case, it also happens to be a wireless local area network, but nonetheless, it is a local area network. Okay, and what that means is all those machines are connected to a common piece of hardware that we call a router or a router, depending on where you are in the world. Okay, so you might have some other machines here. Maybe you have machine, I already used B over there, so I'll use C. That might be also connected to this router somehow. And we oftentimes draw all these machines that are connected on the same local area network or LAN as sort of tapping into the same quote unquote wire. And so because traditionally that's actually how it worked. They were sort of tapping into the same physical medium. Now it's a little bit different. There are some other pieces of infrastructure there, but we can still conceptually draw it the same way. Okay. Now if D, and I'll draw this one as E, if D wanted to communicate with C or A or E, they sort of communicate on this common medium just by passing some messages there between them. And they sort of, there's a protocol that we won't go into in depth in this class, but in terms of how this works, they first sort of announce themselves, and they could, back in the original days, they'd actually send the message out to everyone on this common medium, and everyone would get it. Now, security-wise, you'd think, oh, that's not very smart. But that's the way it was initially done. It was a shared medium, and so if E wanted to send something clear down to D, A and C would also see it, but then D would pick it up and say, hey, that's for me, I'll get it. Okay. Since then, things are a little bit smarter and more efficient, but the same principle applies for passing messages here. You still don't have to go through this piece of information here called a router just yet if you want to, unless you want to go beyond your local area network. Okay. Now, you might say, what defines a local area network? Well, there's a few things to define it. One is the common infrastructure that you can see here, the fact that they're all behind a router. But there is a second component that has to do with addressing, which we'll get to in just a few minutes when we start talking about addressing. And and just to give you a preview, so this is our local area network here. In addressing terms, everything on the same local area network is also part of what we would call a subnet, okay, which means that when we start talking about addressing, they're all going to have very, very similar addresses, or addresses that are close together. Okay, but let's get back to addressing in just a moment. Okay, so now the idea is we get, if we do want to go beyond our local area network, each of these machines knows that it has to go to the router, and the router is going to do some magic to then send it on to the next location. Okay, we call these next hops. So in fact, this router is going to be connected to another router. Okay, and this router, so I'll call this R1, I will call this R2, and so on, until it finally gets back over to the local area network associated with B. Okay, and it might have some arbitrary number of hops in between those to get from, again, if we're going from A to B, then we would go from A, would send it to router 1, this packet, R1 would send it to R2, and so on, all the way until it gets to B's local area network, and then that would actually look very similar to how it looks on A's side, where B might potentially have a number of different computers that are also connected on the same physical infrastructure, and just like on A's side, they have the same subnet. B is also going to have a common subnet. Okay, we'll talk about that again when we get to addressing in just a moment. Okay, so what we've done is we've basically said, hey, A can communicate locally on its local area network. It can also get things out of its local area network by using its router, and then this router knows how to find the next hop, and this router knows how to find the next hop, and so on. Now, it turns out that it's not just about finding, now these routers, there's some smart algorithms that they use to determine the next hop. Okay, and in the end, that's all they really want to know. They want some sort of a table that says, hey, if I have this place that I'm going to over here, then where do I send things next? Okay, and so it would say, oh, for this destination that you're going over to B, definitely go to R2. Okay, and you might say, well, that's clear because there's only one connection here. But the truth is, with the routers, they may have several connections. There may be some other router up here that it's connected to. There may be some other router here, as you might suspect. So there are many different ways to get where you're going in the network. Okay, now this sounds a lot like a graph problem that you might see in some of your algorithms classes, or in some of your early data structures classes, and that's actually very similar. Okay, if you want to know more about how routing works, we can talk about that in my CS 460 class. Okay, but just know there is some way for each of these routers to know, given a destination, what's the next, the direction I have to send this next packet. Okay, and so they all have to communicate somehow to make that happen. Now, the other thing is when we consider this, I've sort of made it look like people just throw routers in there and, yeah, I think I'm just going to stick some router in there. But there is some notion of autonomy and independence in terms of the way the internet is connected. And so it's not simply that we just have this, it does effectively end up being that you just pass it from router to router to router. But in some, in all cases, you're once you, what do I want to say? But what happens is you're passing organizational boundaries as you go. For example, if I want to send a packet outside of BYU's network, and I'm currently on BYU's network, then at some point I have to leave BYU's boundaries and go into some other location. So what you'd see is, let's maybe say that this local area network is all inside BYU, and up until this point up here, and then even as I get up to this next router, which I'll call R3, this is at BYU's network, and then at some point, maybe this is BYU's border router, which means at the very end, this one would have to establish a relationship. BYU would have to establish a relationship between itself and some other entity, another organization. Okay, we're going to use, as an example, we'll say it's Utah Higher Education Network. Okay, and so then we say, okay, well, that's the way BYU gets out to the internet. And the way it works is, that's right, Utah Higher Education Network has their own set of routers, okay, and some sort of network there that they have. And then let's say these are all connected here, okay, something like this. And then BYU at its border, they have to speak some language with this router over here and communicate. And so now you've passed some sort of a network boundary or an organizational boundary, to get to the next place that you're going. Now this happens again and again and again when you're passing packets around the internet and you're going beyond your local area network and even beyond your organization's network. Okay, so for example, let's go one more, and let's say that, I'm sort of contriving this as we go, but let's say that now Comcast, okay, let's say that this is Comcast network down here, and I happen to have my home machine set up on Comcast network, and they happen to connect to Utah Higher Education Network. So now we have another router here. We'll say that's Comcast router, R7, R8, and then maybe we'll go one more and say R9, okay? And these three are connected together. And let's say R6 within Utah Higher Education Network is connected to R7 in Comcast, and now you have one more organization that you have to go through. I'm going to extend my organization such that we have a local area network here, and I'm going to make it look similar to how I did before, and here comes my host B at this point. Okay, so now assuming that's within B, then we would do something like this to get to where we're going. Okay, and so now if I want to go from A to B, I still pass it on to router 1. Router 1 knows what to do. It knows to pass it to router 2, and so on to router 3. And then somehow router 3 has learned that the next place it needs to go is Utah Higher Education Network, and it happens to have a connection there. So now what you've done is we've created these, the internet becomes what we call a network of networks. In other words, Comcast created their network, Utah Higher Education Network created their network, BYU created their network, okay? And they can have sort of autonomy, and all they have to do then is establish some sort of relationship here at the various entry points, okay? And that allows us to speak together as an entire internet when you tie all these things together. Now, some of these networks across the internet are countrywide. So, for example, there are a few networks that we would consider transit networks. That will actually, that their job is therefore to basically, they don't necessarily have a lot of end hosts on there, like, I've shown B down here as sort of an end host, and A and C and D over here as end hosts. Transit networks are really made to sort of be, to pass traffic between other networks. AT&T might be an example of that, where their job is really just to pass for the most part, packets between other networks and provide that what we call transit between them. Okay, but generally speaking, you still have to go through one or more networks to do this. Okay, so now let's talk just a little bit about addressing and how that works. Okay, so similar to, you could look at this and abstract it and say, well, it looks a lot like a geographical map. Okay, here we have some sort of a city, and within that city we sort of do some planning in terms of how you take letters, your mail delivery, and let's say that maybe even everything on a local area network here is on the same street, and so maybe you don't even have to use the postal office if you want to send something to your neighbor. You could just walk over there and drop it off on their doorstep. But then as soon as you want to get it to another part of town, maybe you drop it off in your mailbox, and that becomes your if you had a community mailbox, if we're kind of following the analogy here, then you'd send it to R1, and then the postal service would pick it up and say, okay, I know what to do. I know what to do with that. If I'm going to go to another place in town, then I really need to take it to this other hub, and then they'll take it to their local area network. Okay, so we could think about it similar to that. And then as soon as you leave your city, then they say, okay, well, here's what we do. We have to take it via semi-truck or even plane to get to the next place where we're going, and then they have their own way of getting it routed externally to the next hop, and then that city would then take it and say, okay, well, I'm really going to this other city. And in fact, you could abstract this even more and say, well, this would take us worldwide in terms of sending a single letter. Okay, but that's exactly what we're doing on the internet with these packets. But now if you think about this from the geographical perspective, the reason why all this works is because there's a notion of where things are located. And specifically, we have addresses to determine in our geographical world where things actually go. So it turns out we have the same exact thing in the protocol world, okay, in the internet world. So each one of these machines has a given address, okay, and it's a numerical address. And not only that, but each organization has a set of address space. Okay, you may have heard of an IP address. Let's define that a little bit explicitly. So BYU, for example, let's make this a little bit more explicit, has an address space of 128.187.0.0/16. Okay, now I haven't explained what all of that means is, but in short, what it means is that BYU, anything that starts with 128.187, and I can fill in these last two blanks over here as X's, anything that you put over on these last two sides means that it actually comes to BYU. Okay, so every one of these nodes over here has an address that starts with 128.187. Okay, everything that might hang off local area networks off these other routers that I sort of drawn here within BYU's network, they have something that comes with 128.187. But as soon as you pass to another network, they're going to have their own address space over here, and likewise over here. Okay, so in the end, we have to have some mechanism for actually determining, what address spaces, who has what type of address space, and how we actually get there. Okay, so two things I'll say about that. One is that how do we even determine, what does this even mean up here? Okay, these numbers. Well, it turns out, let me take a step back and let's talk about one of the components of the internet, and that is protocol. Okay, now you guys have all done something like this when you've designed APIs for your classes, or let's say you're working as a group and you say, hey, this function, it expects to take in such and such parameters, and it returns such and such type. It might be a pointer type, might be an integer, but you've come up with some sort of convention. So especially when you're working with someone else and they're deciding, you're deciding how to work together, there's some sort of consistency in terms of what you have established so that they know what to expect. Okay, so it's all about explicitly saying this is how things work. Now, you could say the same thing about if I walked up to you right now and handed you my hand. In the United States, it would be fairly common for you to put your hand back out and shake my hand. But if I went to some other country where that was not the custom, I'd put my hand out, and that would be a little awkward. Okay, they'd probably say, I'm not sure exactly what you're doing, or it might even be offensive in some places. Okay, so that's why knowing the protocol is actually very, very important from the standpoint of programming, like I just mentioned with my example, or even shaking hands. And now we're going to talk about what that means in the internet sense. Okay, so protocols, it's all about establishing conventions and following those conventions so that everyone is consistent in their communication. Okay, so now thinking about that for just a minute, okay, if I were to send a bunch of bytes over, let's do this, just the case from, to simplify things, we'll say A is sending some bytes over to C, okay? They would have to have some way of knowing, what they're expecting, right? Are they expecting an image file? Are they expecting keystrokes? Are they expecting something else, some sort of console type characters that are coming through? Okay, it's hard to tell unless they've established that ahead of time. So here's the deal. What we've established is, and I'm going to write something on here. I've got a sheet of paper, and I'm going to write a message. Okay, and it doesn't matter what my message is, but for the sake of illustration, I'm going to go with something that you all will understand. And it is this. Hello world. Okay? So this is my message that I'm going to be sending. Okay? Now here's the thing. Rather than just sending this, we want something that rather than just sending, okay, here's hello world from A to C, that means you have to come up with some custom protocol to even get it there. And we've just talked about addressing, so obviously we want some way to identify, okay? So what we're going to do is, instead of just sending hello world, we're going to add some additional information at the beginning of that, okay? And so what we're going to do is, we're going to take hello world and we're going to put it in an envelope, okay? This is symbolically speaking here, because what we'll really do is adding on some bytes that we would refer to as a header. So it's going to come before any type of message of bytes of any type that are going to come in here. In my case, it's hello world. Okay, so here we have our header, and there are some important things that we want to put in that header. Okay, so first thing I'm going to do is I'm going to add an address for this. And so here I'm going to say, and let me go to my geographical example for just a minute. So I'm going to say this is coming from TMCB in Provo, Utah. Okay, and I'm going to say this is destined for Tom's Toys in Ventura, California. Okay, so now you can see when I pull this envelope up, here's what we have. Okay, we still have the original message, but we've put something on the outside that has our from address, okay, and it has the destination address. Now, when we send something from A to C, C has some conventional way, and again, in our human world, we would receive this and we'd say, okay, we can look at this and say, okay, yeah, this is the right destination, and then we can remove the envelope and actually get our message that we were looking for. We can sort of discard everything that came with it. Okay, and you can also say, even if it was just going from A to C, now we've made something so portable that we have our ultimate destination, and you could actually say, okay, if I'm sending this to my post office, okay, and getting out of my local neighborhood, I send it to my post office, and they can say, oh yeah, it's going to Ventura, California, so clearly, I know where to send that next. I need to send it to my next hub, and eventually it gets out of the city, and the city says, oh, I know where that goes. It's going to go to Los Angeles first, and it's going to take it here, and then it's going to take it to this section over here, and eventually it'll get to where it's going, and then the other side can pull out the message and say, here's what I was looking for. Okay. All right. So again, the idea of protocols and the idea of portability, okay, means that whether you're sending from A to C or within my local neighborhood or even local area network, it should be just as portable as if you're sending somewhere way far away, and you need some identifying information to help us with that. Okay, so that's why we put on this header. Okay, so now let's make that just a little bit more computer science centric. And so what I'm going to do is, on this outer one, I'm going to establish something here. So I'm going to say 128.187.82.4. Okay, and then on the other side, I'm going to say 134.252.4.1. Okay, so now I have, and yes, it didn't fit all in one line, okay, but what we have is a source address and a destination address, and so numerically, we can also say, okay, I know where I'm going now, so when it goes, I can say, is it going to any of my local partners, in which case the address would have been really close together. There's some way of defining that. We'd say it's within a subnet, but if not, it knows to go to its router, and its router would say, oh yeah, 134.252.4.1. I know I'm supposed to send that one to R2, and so on to where we're going, so it eventually falls to the ultimate destination. Okay, so having that information, let's get back to this idea of what these addresses mean. Okay, now that we have a little bit of background. Okay, so what this means is, it turns out we're establishing this protocol, and I've sort of abstracted that into an envelope. But remember, these end up just being bytes. We've had a packet of data, okay, that contains the hello world, and let's assume these are just characters. It's actually literally these characters that we are sending across, but we want some sort of encapsulation. So when we get these, whether it's C receiving or whether it's R1 receiving it, they need something to look at, and they need to know, for example, how many bits how many bits does an address consist of, and where within this envelope header does the address actually start. So let's say, the first, for example, let's say the source address starts at offset 4 in terms of bytes, and then the next 4 bytes are addresses, and the next 4 bytes after that, starting at offset 4, the next 4 bytes are the source address, and then after that, the next 4 bytes are the destination address. Okay, once you've established something like that, then when any node in this entire network is reading this envelope, it knows where to look for the byte sequence that will tell it the information that it needs. But otherwise, remember, it's just a bunch of bytes. Without the protocol conventions that we've talked about, they don't know how to interpret it. Okay, so what we've done is, in terms of putting all this together, when we take all this stuff together and we say, what's a protocol? We've defined something called the Internet Protocol. Okay. An Internet Protocol is effectively our envelope. Okay, the Internet Protocol establishes what happens in that envelope, so to speak. You might have also heard this abbreviated as IP, which is where the term IP address comes from. Okay, so when we establish that header is just a series of bytes that are known to this node and this node and this node and this node. And in fact, when you look at it, we can in fact say that there is some offset at which the source address starts. Let's say this is 4 bytes long, this header that we're looking at. And so here you have 4 different bytes with different values that mean different things. And then here we say is our source address, and then here is our destination address. Now I'm not actually following the spec here right now. I'm not using that. I'm sort of illustrating how it might work. So this is for illustration purposes only at this point. So these next 4 bytes, we would say, would be the source address. These next 4 are the destination address. So now, when this machine is actually reading this, it can say, oh yeah, I can totally start at offset 4, read these next 4 bytes, interpret that as an IP address, and do the same thing with the destination, interpret the next 4 bytes after that as an IP address. So because you have to have protocol, now I've set all this up to explain what this address up here means. What it is, in the Internet Protocol, what they defined was 32 bits or 4 bytes of information per IP address. So when we talk about addressing, every one of these has to have an IP address that's 32 bits because that's the size of the address inside the header that has been defined, okay, on the envelope, but more specifically in the actual protocol. So now when you're reading bits off the wire, you can say, I know exactly where to go to find the source address, the destination address, including where to start and where to end. Okay, so now when you look at this, you might say, well, that just looks like a bunch of decimal numbers. That is true because that's how we represent it. Okay, but in other words, we call that presentation format how we look at it. But in the end, if you take all that away, okay, this 128, 187, this is just a bunch of bits. In fact, each one of these values between the dots is the decimal value corresponding to the 4 bytes of the IP address. Okay, so up here you can see I have 128, 187.x.x. but in the end, the 128 is actually the bit value, excuse me, the decimal value for the bits in this first one. 187 is actually the bit value, the decimal value, excuse me, of the bit value that's in this second one. And then these ones, which I said are arbitrary within BYU's network, these are some value also for 8 bits. Now, because these are 8-bit values, that means that all IP addresses, each of these things between the dots, okay, each one of them only consists of 8 bits, which means that the maximum value that they can be is, that's right, 255, okay, because it goes from 2 to the 8th. Sorry, we've got, if we have 8 bits, let me just clear out a little bit of space here, okay. All right, so if we clear out a little bit of space, we can say each one of these is 8 bits, 8 bits, 8 bits, 8 bits. And so each one of those, there's 2 to the 8th possibilities, and specifically a range of 0 to 255. So the highest IP address that you could see would be 255, 255, 255, 255. It turns out that's a reserved address. You can't actually use that one. But the point is that's the highest value you would see in there. You would never see 256. That doesn't make any sense because you can only represent each octet with 8-bit values. Okay. All right. So this is what we would call the Internet Protocol. Now you might be curious at this point, who hands out all this stuff? And when we talked about this addressing, we did talk about that there are different organizations. You know, we have BYU here with their own addressing. We have Utah Higher Education Network with their own address space, Comcast with its own address space. Kate, how does all that work? Okay, so to describe where we get our addresses, where various organizations get their addresses, here's how it works. We have something called the IANA. Okay, the IANA stands for Internet Assigned Numbers Authority. Okay, and what happens is they're sort of the central figure in the internet in terms of assigning those numbers, but they have some helpers along the way based on geographic region. So IANA starts out, and again, there are, if you think about all 32 bits of address space, that means there are roughly 4 billion possible IP addresses. Okay, so what they do is they lump them out into lumps, similar to how BYU had 128.187.x.x, so anything starting with that, they'll sort of give that chunk of addresses to one organization. But it's not actually the IANA that does it directly. So here are their helpers. Okay, they have what are called in between regional internet registries, okay, or RIRs. Oops. RIRs, okay, regional internet registry. And here's what happens. So we have one here that is the one for United States and Canada, and that's called ARIN, which is the American Registry for Internet Numbers. Okay, and then we have one in Europe that's called RIPE. Don't ask me what it stands for because it's French and I wouldn't be able to pronounce it. Okay, there's one for the Latin American region, which is called LACNIC. Okay, there is one for the Asian Pacific region, which we call APNIC, and that covers Australia, China, Japan, and all those areas in the sort of Asian Pacific region. And then finally for Africa, we have AFNIC. Okay, so these 5 ones. So what IANA does is it'll hand out, it started with the 32 bits, okay, and it'll basically hand out in chunks as needed to these different groups. Okay, and then they would in turn hand them out. For example, we would get ours, BYU got ours from ARIN back in the 1980s. Okay, so they would then hand them out there. Now here's the thing. Okay, we have 32 bits of address space, which means 2 to the 32 possible addresses, or roughly 4 billion. Well, what happened was all of those have effectively been given out already because it wasn't a big number. And in fact, when this whole thing started, it sort of went away. It sort of grew a lot faster than people were expecting. And so they thought, that wasn't, things went a lot faster than addresses. What do I want to say? The internet grew a lot faster than folks were expecting. So those 32 bits went very quickly. And so years later, and not many years later, they started looking into what they should do for the expanded internet, which would require a lot more address space. And so what happened was they took those, the IP protocol, and they actually versioned it. So one of those fields in this header, one of those fields in the header here is actually a version number. And so not only do you have to determine, where is the source and where is the destination within a given IP header, but also depends completely on the version, which is one of the first bits in the header. And so you'll read it and say, oh, which version have I been looking at? If it's such and such version, then it starts right here. If it's another version, then it starts right here, and that's where you go from. Okay, so it turns out that originally we were working with a version that we called IPv4, or IP version 4. And that was the one where you had the 4 bytes of address space for source address, 4 bytes of address space for destination address, and that's where we were. But the next generation one that they were working on, and I say were, but we're still in the process of trying to figure this out and how to deploy this thing, is IP version 6. Don't ask me where the 5 went, okay? I don't know the answer. It's probably somewhere deeply rooted in the standards communities, and I simply don't know that history. Okay, but as it is, we do have another protocol version that we're trying to extend because we've reached our limits. There are ways that we've gotten around that, which we go into more depth in CS460, but in this class I'm sort of waving my hands just a little bit. We might talk about it at some point, how we've gotten around and sort of made IPv4 last a lot longer than it has. But the short version is that IPv6 was intended to replace it, but it's had a very, very difficult time along the way in terms of where we're at. Okay, so that was a sort of long background to go along with where does address space actually come from? Well, there is some central group that's sort of assigning it, and then regional groups that further delegate it down. But in the end, that address space all depends on a protocol, which is the IP protocol. All right, class. Now we're going to just take a look and use some of our available tools to help us better understand this notion of internet connectivity and addressing and communication between different nodes. So first of all, let me show you. So I'm running on my local machine here, and I have an address that if I run this IP adder command, now I'm going to, for the sake of time, skip over this first interface over here, which is what we call a local or loopback interface. And this is the one that will actually take me out of the internet. Okay, so what you can see is here's the address that I have. Okay, I realize we're sifting through it, a few different items here. It shows a lot of output, this command, but I wanted to show you this is the address right here, 10.0.2.15. Okay, so that's the address of my current machine that I'm on. Okay, I'm going to clear this and I'm going to go back to my main screen. And now I also happen to be logged into a remote machine in one of my other tmux panes. And so this one that I'm logged into remotely is called Roam. Okay, and when I look at this one, I have, here's my address that I'm looking at, 71.19.157.153. Okay, so two different addresses, and one of them happens to be here in my office at BYU, and the other one happens to be in a different region across the internet. Okay, so now what I'm going to do is I'm going to clear this out. That was just to demonstrate to you what I had in terms of two different machines. So top pane is my local machine, middle pane is the machine that I'm attempting to communicate with on the other side. So let's do this. On my remote machine, I'm going to start up a simple process that's called netcat. Okay, so netcat's job is to listen, and I'm not going to explain what I'm doing in terms of command line arguments right now. You're just going to have to go with me, and I'm going to explain this in a later lecture. But first of all, what I'm doing is I'm setting up some way for it to communicate. Okay, very simply, and all netcat does is it listens for incoming communications and then it prints them out to the screen. Okay, so I'm sitting there waiting, and what I'm going to do, netcat on my version simply will send out a something that let's see, it takes standard input and will send it. So I'm actually going to use my pipe functionality. I'm going to say echo foobar, and then I'm going to put that to netcat, sending it to the other side. And I need to do this, dco.net. Okay, now there's something in between that we're going to talk about later that translates this name to the IP address, but I'm sort of doing this in between. So an IP address could go through here equally well, but I'm choosing to use a name, and then there's some magic that's going to happen to translate to that to the remote IP address. Okay. Now, before I actually hit enter there, I'm going to skip down to the bottom pane. Okay, so down here, I'm going to start up a process. TCP dump is my friend. It's a program that sits there and listens for outgoing packets or even incoming packets on the wire. And I've put in certain criteria to only filter for things specific to what I'm looking at. So don't worry too much about the command line arguments, except we're going to examine the packets that are going out or coming in related to these communications here. So you can see here I am listening now on the bottom. And now with all that set up to listen, I'm going to take this up at the top and hit enter. So you can see I hit enter, and then the next pane down, which is again my remote host, it received this message that I'd sent, foobar, and just printed it out to standard output. That's what netcat does. So a very, very simple program, but again, just illustrating the connectivity. Now let's look at what was actually sent, okay, in terms of what actually hit the wire, this sort of outgoing interface, and what things looked like as they were leaving my computer through my network card. Okay, so if we look over in the right, there's three columns here. One shows where you are in the byte sequence. So this is again referring to sort of that envelope that I showed you earlier. This is the index into that envelope. Okay, so we have 0000, 0010. Okay, so we're starting at this point at byte number 16, and at this point we're starting at byte 32, going down with each row, which means that the first bytes that we come across up until, and then, well, actually, let me show you this third column over here. This actually shows, where possible, the ASCII representation of that byte. So you'll start to see some familiar characters if you look on the far right and the second row down. In other words, these last four characters over here, FOOB, that's the foobar that I sent. Okay, and then you would see that the new line is actually that last period on the bottom line. So you see FOOB, AR period. So if we count back here, here's the B right here, the hexadecimal 62, hexadecimal 6F is our O, 6F is another O, and then 66 is our F. Okay, so everything from here to the end is our actual, that's the hello world that I sent in the envelope earlier. But now you might be wondering, okay, well, what is all this stuff before then? The DB, the F0, and starting clear up here at the hexadecimal 4500. That is that header information that we talked about earlier, okay, with the envelope. And in fact, if you were to look right here at this 45, okay, this 45 right here is in fact the the 4 part of it is the version, the IP version that we talked about earlier. That's to tell any machine that receives this packet along the way, oh, we're speaking IP version 4 here. Okay, if we skip over just a little bit, just so you can see this, we have 10.0.2.15 is my IP address. Okay, up here, this is just the meta information that TCP dump is showing us. But if we look at the actual packet, we can see down here a hexadecimal 0A, 00, 00, and then 02 and 0F. And if we convert all those to decimal, each of those 4 bytes, turns out those come up to 10.0.2.15. Pretty cool, right? So that's part of the envelope information. There's some more decoding we could do, but I just wanted to give you a sample of what's going on there, okay? So we send a message, and on the other side, it's received, and the other side does something with it. And of course, communications can be 2 ways. This is just to illustrate a point. Let me do one other tool here, and what I'm gonna use one other tool that is called Telnet. Okay, so what I'm going to do now is I'm going to get rid of this. I'm going to get rid of this. Okay, I've gotten rid of the second window. So now I'm going to take this, and I'm going to use a tool called. I've gotten rid of the wrong window. I'll do that. Okay, so now I'm going to use a tool called curl. Okay, you're going to become very familiar with curl as time goes on. and as you start doing one of your labs. But for right now, I'm going to use curl just to show a point here. What curl does is it simply opens up a connection to a web server and asks for a given resource. Okay, so what I'm going to do is set up a filter here. Okay, and now I'm going to do this. Okay, so I'm going to hit enter here, and what this is doing, again, I'm opening up a, I said a connection earlier, but I'm sending some sort of a communication to this machine called www.notls.iml.byu.edu. And of course, there is an address for that. I didn't look it up. Right now, I'm having some magic happen for me behind the scenes. Okay, but here's what happens. Okay, so if I take a look over here, and I'm going to sort of scroll backwards a little bit. And so if I come back here, I want you to notice a few things. There's a lot in here, but what I want you to see is, remember I said that different messages the messages are broken up into different packets. Well, it turns out there's a lot of information here, and what I'd done with that curl command, that when I ran that program, it connected and it sent something here. Okay, so I want you to look at one of the early packets here. Here's one packet. You can see it's leaving my host 10.0.2.15, and it's going to this location that I had specified. Turns out this is www.notls.iml.byu.edu. So it had done, it's sending this information, and here's what it sent. It sent something, you can actually read these characters over onto the right. Get, there's a slash there, these are spaces in between. HTTP, there's some other information in there, something about a user agent, okay? But the point is, it's actually sending some sort of request, and you can see it in in ASCII characters there that are represented. Okay, so as once the other side gets that, you can see here's a packet in terms of response that gets returned from that address now coming to my address. Now, if you remember the netcat communication, it was one-sided. I sent it something, it printed it out to standard out, and we were done. That was it. Okay, and this side, this is a what we would call a request response protocol, but the point is I'm sending it some packet, and it's sending me some information back. Okay, that's established, but somehow this is making it from my machine to the other machine, and then this response is coming back from that machine back to my machine. You can send it. You can see it sending me all sorts of information here. We've got the HTTP. It says something about HTTP in there, which we'll talk about that protocol later. It says something about a date. You can see the date in there is today's date and a little bit later time. Some other sort of meta information, and then you can also see this this information here, which if you've done some work with web pages, you can see this is actually HTML. Okay, it'll start here. It'll say something, about the title. You can see the title is the Internet Measurement and Anti-Abuse Laboratory. Okay, we keep going down. You'll see some more information about that's actually part of that page, including something about myself and information about it. Now keep going on. I'm not as interested in you looking at the content, but what I want you to see is this was one big page of information. Okay, one big HTML page. But just like I mentioned at the very beginning of this lecture / screencast, what happens is it had to break that page up into multiple packets. So you can see, actually looking at this one right here, this is a second packet where the information simply continues. Okay, you get past this envelope information. Again, it looks very similar to the information that we saw earlier when I examined the packet earlier. You have a bunch of envelope information up at first, and then eventually over here, I'm looking now at the right side where you can interpret it. You can see some more HTML. So after you got past the envelope, you're simply sending more data in the communication. So it's just another example of how we had this big thing, and then we broke it up, big message, and we broke it up into different packets, and each one of those packets was given an envelope with identifying information to get it from host A to host B and back again. So in this case, I'd sent some information to one side, and it had come back and returned the information that I had requested back to my host. And that is a summary for us today, a good starting summary in terms of our communications basic internet overview. And we'll start talking next time about more specifics of internet communications at the next class.